Thank you very much. So this second lecture is about operator ideals and the Moore-Penrose inverse. We will study the Moore-Penrose inverse as a map between certain infinite dimensional homogeneous spaces associated to operator ideals. So we start with some definitions. Again, H is a separable complex infinite dimensional Hilbert space, and B of H, the algebra of bounded operators on H. Recall that from our first lecture, we define operator ideals as two-sided ideals of this algebra of bounded operators. But now we will stick to a smaller class of operator ideals because we will need a norm to construct then some Banach manifolds. So the class of operator ideals that we will deal with in this lecture will be the symmetrically normed operator ideals. These are two-sided ideals of B of H satisfying the following three conditions. Here, an inequality between the norm of the ideal and the usual operator or uniform norm. Then a normalization condition for every rank 1 operator. And then the fact that the ideal is a Banach space with its norm. And we also consider only proper symmetrically normal operator ideals. Some examples here, the compact operators, the P-Schatten classes for P greater or equal than 1, and the operators ideals associated to symmetric norming functions that we defined in the first lecture. We recall the following remark by Kalkin. Every operator ideal must contain the final rank operators and is contained in the compact operators. So in the setting of bounded linear operators, this is the definition of the Moore-Penrose inverse. An operator E dagger, a bounded linear operator, is said to be the Moore-Penrose inverse of A if the following four conditions hold. The notation E dagger is justified because if it exists, then it is uniquely determined. And for the existence, we need to consider the following set of operators, the set of closed range operators. These are operators such that their ranges are closed subspaces of the Hilbert space. We have this fact here. An operator has closed range if and only if its Moore-Penrose inverse exists. The converse is more or less trivial using this first condition here and the fact that we are dealing with bounded operators. And for the forward implication, we write A0 to this restriction for the orthogonal complement of the null space to the range due to the open mapping theorem. This is an isomorphism. So the Moore-Penrose inverse can be seen to be defined as follows: the usual inverse of that operator, and then in the other part of the space is 0. Some properties of the Moore-Penrose inverse. As usual, we write P sub S for the projection onto a subspace S. Then here, the first condition will be important in our talk. E dagger, A dagger A is indeed the orthogonal projection onto the complement of the null space. And then A dagger is the projection onto the range of the operator. The Moore-Penrose inverse is relevant because it is related to linear systems like this. We have that one can give a parameterization of all the solutions using the Moore-Penrose inverse as follows. And also it provides the unique solution of minimal norm. Here in item 3, we have some elementary properties about powers with natural numbers, about the adjoint, and also if we take the Moore-Penrose inverse of the Moore-Penrose inverse, we get again the operator. And here in the fourth item, we have that this property in general does not hold. In fact, the product of two bounded linear operators with closed range may not have closed range, but here in this case, when the operators commute, this property holds, and there is a result by Boulding that gives a complete characterization in the case that we assume that the three operators have closed range. Are these ranges inclusions? Note that here we have an adjoint, and also here that will be important later. So what we want to do in this lecture is to try to understand perturbations of the Moore-Penrose inverse. This is very natural in the finite dimensional setting. There are several works dealing with perturbations of the Moore-Penrose inverse between matrices, because, as we said before, the Moore-Penrose is linked to the linear systems. So we will like to understand perturbations, but now in an infinite dimensional setting, in the setting of operator ideals. We fix an operator A and a symmetrical norm ideal S here. And we look at these sets. This is the set of closed range perturbations by operators in the ideal of the fixed operator A. We have to assume that the perturbations have closed range, because then we want to take the Moore-Penrose inverse. And in this set, we put the following metric. Note that in this set of perturbations, every operator is of the form A plus something in the ideal. So the A cancels, and this metric is well defined here. So we want to study the Moore-Penrose inverse. From now on will be denoted as follows, as mu, in this set of perturbations. Some of the tools we will use are the index of a pair of projections and the theory of infinite dimensional Lie groups and their homogeneous spaces associated to operator ideals. So we first try to understand the continuity of the Moore-Penrose inverse. We start with the finite dimensional situation. It is well known that the Moore-Penrose inverse in matrices is not continuous. Here we have a simple example. Take these 2 by 2 matrices, diagonal matrices. The Moore-Penrose inverse is as follows. So Bn converges to B, which is here B, obviously, but the Moore-Penrose inversely, of course, does not converge because the norms of these matrices become arbitrarily large. So to understand the continuity in the setting of matrices, the following formula by Wedin, this is from the 70s, more or less. It says that the difference between A dagger and B dagger can be written in terms of the difference between A and B, and also there are joints and some other products here. So a little of work. After a little of work here, we can find this estimate. So suppose that B is approximating to the matrix A. In order to have that their Moore-Penrose goes to 0, what we have here is to bound the matrix B dagger, which appears here and also here. So the result of Wedin is as follows: a sequence of matrices converging to another matrix B. Then the following are equivalent. B and dagger converge to B dagger. These norms are bounded, and also the null spaces are equal for all n large enough. Note that here in the example, we have different null spaces. And this condition, sorry, here is the nullity, the dimension of the null spaces. This condition on the nullity, we can change it for a condition on the ranks in the final dimensional setting. So these parts here that are written in blue will change now to understand the infinite dimensional situation with bounded linear operators. We have the following result by Isumino, a sequence of closed range operators converging to another closed range operator. Then we have the same two conditions here that are equivalent, but the condition on the nullity now is changed to this condition for the projections onto the null spaces. So we want to understand the continuity in the setting of operator ideals. Again, the notion of index of a pair of projections that we defined in the first lecture will be useful. Recall that a pair of projections such that this operator QP viewed as an operator from the range of P onto the range of Q is Fredholm, then the index of the pair is defined as the index of that operator and it also can be computed as the differences of these two dimensions. So to begin with, we have the following property. Suppose that we have two closed range operators such that this difference belongs to the operator ideal. Then we can prove that the index of these projections onto the null spaces is well defined. In fact, we have to use Wedin's formula, which writes A dagger minus B dagger in terms of A minus B, and here the adjoint of A minus B, also here, operator ideals are closed by taking adjoints. So we find that A dagger minus B dagger belongs to the operator ideal, and then we write the projections onto the null spaces using the Moore-Penrose inverse here, which can be also written in terms of B dagger minus E dagger and B minus A. So this is in the operator ideal, and then we easily can get that the pair is indeed a Fredholm pair, so the index is well defined. Our result about the continuity of the Moore-Penrose inverse is as follows. Note that here we have convergence in terms of the operator ideal. We have here the same two equivalent conditions, but now the first one is with respect to the operator ideal norm. And now the last condition is in terms of the index, because of our previous property. When this difference Bn minus B is in the operator ideal, this index is well defined and it can be used to give a characterization of continuity. So we next use the previous characterization to understand the continuity sets of the Moore-Penrose inverse as the map in our set of perturbations of the fixed operator A. We have two remarks below. We will need to introduce the following Banach-Lie groups associated to operator ideals. In our first lecture, we used the unitary group associated to an operator ideal. Of course, there is a version for the invertible group. Here, we denote GL sub S. It is a Banach-Lie group in the topology defined by this metric in terms of the operator ideal norm. And we recall again the restricted unitary group, which is denoted as follows. And a remark that will be useful here is that both groups are connected. In fact, the exponential map is surjective by using the analytic functional calculus. So we can always get a path, a continuous path, showing operators in those groups to the identity. Our second remark is again related to what we studied in our previous lecture. Recall this Stiefel type orbit associated to partial isometries and operator ideals. Recall that given two partial isometries, there is a unitary satisfying this condition, sending the partial isometry V1 in the partial isometry V2, if and only if these two conditions here hold. So after some work, we were able to generalize this to close range operators, and instead of having the unitary group, the restricted unitary group, we will have the invertible restricted unitary group. So this condition GA equals B is equivalent to these two conditions here. And moreover, this can also again be generalized to the case where the null spaces now are also moving. Instead of move with the group only the range, we can move also the null spaces. This is the action here with the invertible restricted group. So now the null spaces are changing, and the equivalent condition to an operator, a closed range operator, having this form is given in terms now of the index between these projections onto the null spaces. So now we will use these remarks to understand our set of perturbations here. Recall that A is a fixed closed range operator, and also we have a fixed symmetrically normed ideal S. Our set of perturbations turn out to be decomposed as follows. Recall that operators here in this set of perturbations have a well-defined index between the projections, the corresponding projections onto the null spaces. So we can use that index to give a decomposition of our set of perturbations. We will call each of these sets Ck of A. The K comes here from the index. And it can be shown that the union here is taken with respect to some set, JA. We can completely describe that set, and it turns out that in our setting of an infinite dimensional Hilbert space, there are always infinitely many of these sets Ck of A. Some properties of these sets are the following. Using our characterization about this type of actions moving both the range and the null spaces, we can show that this Ck of A admits a transitive action of the product invertible group associated to the operator ideal. As we said before, these groups are connected, so it is an immediate consequence that these sets Ck of A are also connected. Then we have this property, the distance in the operator ideal norm between any two of these sets turns out to be 0. This can be proved using properties of the index, and moreover, each of these sets turns out to be dense in our set of perturbations. It can be shown using our previous result about continuity, which is related to the index of the projections onto the null spaces, that this map, the Moore-Penrose inverse, restricted to these sets, which are indeed orbits, turns out to be a locally Lipschitz map. This is, again, a consequence of Wedin's formula. And we have here the last property is a sort of maximality property, because if we have another set, C, which contains our orbits, and it is contained in our set of perturbations, and suppose that mu is continuous on this set, then we must have that C is exactly Ck of A. So this is a decomposition of our set of perturbations with all of these properties. We will use that properties to now study the differentiability of the Moore-Penrose inverse. So far, we have understood the following. The index of paired projections gives the continuity of the Moore-Penrose inverse in our set of perturbations. Recall that in the finite dimensional situations, we can use the nullity or the rank. So our condition now in the infinite dimensional setting associated to operator ideals can be interpreted as a sort of rank with respect to our fixed operator A. Also, we have that the continuity sets Ck of A are indeed orbits of an action given by a Banach-Lie group. So it is natural to ask the following question. Can we now use that to obtain differentiability results about the Moore-Penrose inverse? That is, use the structure of these Banach-Lie groups, understand that orbits as homogeneous spaces, smooth homogeneous spaces. So let me show you first what was known in the case of bounded linear operators. This is a result by Korach, Mastripieri, and Mbekta. Note that here we have this notation, dn of E and B is this metric that considers the operators and also the distance between the projections onto the null spaces. So the result is as follows. They consider these orbits, which these are versions of our orbits, but instead of having here the restricted invertible group, this is the full invertible group. So they prove the following. The map pi here induced by the action turns out to have continuous local cross sections. But an important fact here is that they put in the orbits the topology given by this distance, dn. There is also an analogous version of this result with a distance between the projections onto the ranges. But the reason that they must put here the distance dn is that to construct the local cross sections, you need to use the Moore-Penrose inverse. So you need to control in some way the projections, and the result by Sumino gives a control of that projections. You need that the projections onto the null spaces are close enough to get continuity of the local cross sections. And the other part of the result is that these orbits are smooth homogeneous spaces of this product group. They prove that the isotropic group is indeed a Banach-Lie subgroup. So these orbits then become a smooth homogeneous space. A motivation for considering this type of action, moving the null spaces and the ranges, is here. This action was considered in a well-known paper by Halmos and McLaughlin about the geometry of partial isometries. But in this case, instead of the invertible group, we have the unitary group. This action in the set Pi of partial isometries of a Hilbert space have a nice property because the components, the connected components, are given by orbits of this action.
Sorry, Eduardo, can I ask a question? Do you hear me?
Yes, of course.
Can you go back to this slide? I wanted to ask if this stabilizer is complemented or...
Yes. The notion of Banach-Lie subgroup that I am using is that the isotropy group is a Banach-Lie group in the topology of this product group in the same topology, the uniform topology, and the Lie algebra of the isotropy group is closed and complemented in the Lie algebra of this group.
Okay, thank you very much.
So I will now mention some other works that are related to our work and also motivates our work. In the finite dimensional setting, there is a work by Golub and Pereira, where they compute the directional or Gateau derivatives of the Moore-Penrose inverse, putting the constraint that when you take the incremental quotient to get the derivative, the perturbations must do not change the rank of the matrices. Then there is this work in the setting of C-star algebras about generalized inverses by Andrew Korach and Mbekta. They studied the differential structure of the set of generalized inverses in the setting of C-star algebras. Generalized inverses are defined in terms of the first two conditions of the Moore-Penrose inverse. Then I would like to mention this paper by Beltita, Golinsky, Jakimowicz, and Pelletier about Banach-Lie group poise and the Moore-Penrose inverse. In the last section, they have some results about the Moore-Penrose inverse related to Banach-Lie group poise, and they propose to study differentiability properties of the Moore-Penrose inverse in more general Banach algebras. And then the last work here by Beltita and La Rotonda. What I would like to mention about that work is that they considered unitary orbits given by restricted unitary groups of associated to operator ideals. And to get the condition in order to that orbits are submanifold of the natural ambient space, they show that the operators must satisfy some spectral condition, which is that they must have finite spectrum. So now I will give our main result about the differentiability properties of the Moore-Penrose inverse. Suppose again that A is a fixed closed range operator and also S is a fixed symmetrically normed operator ideal. We have that this map by K for each K, recall that these sets Ck of A defined in terms of the index of pair of projections. These sets are orbits. So this map induced by the action, we prove that this map admits continuous local cross-section. I would like to point out here that the topology here that we are considering is the natural topology in this setting, in contrast to the result by Korach, Mastripieri, and Mbekta in the setting of all bounded linear operators, where they had to put a metric involving the projections onto the null spaces. we don't have to put such kind of metric here because in these metrics, in these orbits given by restricted group, the index is a sufficient tool to control the continuity of the Moore-Penrose inverse. Then we have this fact: our orbits Ck of A are real analytic homogeneous spaces of this product of the restricted groups, and also they are real analytic submanifolds of this natural ambient space. Note that here we are also using a sort of a spectral condition that I mentioned is required in the work by Beltita and La Rotonda in the case of unitary orbits. In our orbits, note that these are orbits of close range operators. So there is a characterization of close range operators in terms of the spectrum. We have that a close range operator, we have that an operator has close range if and only if 0 is not in the spectrum or it is an isolated point of the spectrum. So behind this result, we have also a sort of a spectral condition to get the submanifold structure. And our last result is that if we restrict the Moore-Penrose inverse to our orbits, then it takes values on the corresponding orbit here, Ck of A dagger, and this can be shown to be an analytic map, which obviously the inverse is again analytic. I will try to give some ideas in the proof of these items to finish the talk. First, we look at this picture here. In the left side, here we have our set of perturbations. We can imagine that this set is decomposed as by these lines. These lines represent our orbits. I put the blue color here for the orbit C0. Note that orbit C0 is the orbit where the operator A lies. Then these lines are mapped by mu to other lines here, which are again orbits. Now we have here the following set of perturbations of the operator A dagger. So when we restrict our map to these lines, which are indeed Banach manifolds, our map mu turns out to be analytic with an inverse that is also analytic. Some ideas we can assume to prove the first part about the continuous local cross-sections. We may assume that K is 0 and we construct a local cross-section at our operator A. That means that we need to find a map from an open neighborhood in the orbit to this group, satisfying this condition. The important fact here, I wrote all the details, but please go to here. This is the definition of the cross section. It has two coordinates. The first one is here and the other here. Note that B is moving and A is fixed. And we have here the projections onto the range of B and to the null space of B. So these projections can be written in terms of the Moore-Penrose inverse. And if we restrict our map to this set above here with the condition in the norm of the operator ideal, we get that all the projections have zero index between them, and we get the continuity of the Moore-Penrose. So we then obtain the continuity of this map, sigma. For the second part, the homogeneous space structure, we can compute the isotropy group as follows. And again, in our constant, in our setting of operator ideals, we can prove the same result as Corach, Mastripieri, and Mbekta in the setting of bounded linear operators. This isotropy group is a Banach-Lie group of the product group. So the orbits, which are in bijection with that quotient, turns out to be a real analytic homogeneous space. Then to understand the submanifold structure, we put here P, the projection onto the range of A, and Q, the projection onto the complement of the null space of A. The tangent space at the operator A can be computed as follows. This XA minus AY. And using this projection here, P and Q, we can give an operator matrix description of the tangent space. So this now can be easily seen to be a complemented subspace, because one have to fill this entry here to get a supplement, a closed supplement. So we get that tangent spaces are closed and complemented in the ambient space. So then, using the first item about the continuity of the local cross of the map induced by the action, we can also show that the inclusion map is indeed an embedding. So we get that C0, and the same is true for all the other orbits, are submanifolds of this affine space. And the last part about the analyticity of the Moore-Penrose inverse. Some ideas are the following. Again, we study the case of K equals to 0. So we have this map from this orbit to this orbit. We have to take the Moore-Penrose inverse of these three products here of operators. Recall that this property does not hold in general. So to study the dependence of this map in terms of the operators, the invertible operators, G and K here, we have to prove the following lemma. Suppose that we fix S, a closed subspace, then we can construct the following map between the invertible group associated to the operator ideal to the unitary group associated to the operator ideal that satisfies this condition here. T of S is the same as U sub T of S for our fixed subspace S. We need some technical work to actually prove this fact, but this is the key to understand later the analyticity of the Moore-Penrose inverse. We apply these results to the following subspaces. Here S will be the orthogonal complement of our fixed operator A. So we have a map UK, and here S, the subspace S, will be the range of the operator A. So we have another map UJ, and another important point here is the following property for unitaries and the Moore-Penrose inverse. Recall that in the property of bolding, the characterization of when one can write the Moore-Penrose inverse of a product as a product of two Moore-Penrose inverses. In that property, some adjoints appears, so that property holds for unitary operators. So we have that this condition in blue holds for the Moore-Penrose inverse, and we use it here to rewrite the Moore-Penrose inverse of elements in our orbits as follows. We can write here and end with here in this line. Note that we have UK, which is an analytic map in terms of K, of the invertible operator K. We have here the star of UJ, which is again a real analytic map in terms of the operator J using our lemma above. And here we can find a matrix decomposition such that the 1-1 entry here is an operator from the range of A to the range of A. Moreover, it is an invertible operator. So here we can use that the inversion between a real Banach-Lie group is a real analytic map. So using this factorization, we have written the Moore-Penrose inverse in our orbits as a real analytic, as a product of three real analytic maps. Then we can pass to the orbits using that we have a real analytic homogeneous structure. So our homogeneous space admits real analytic cross sections. So we can conclude that this map between orbits is in fact real analytic. I will end with these references. Here is the article by Andrew Cho, the article by Beltita and La Rotonda, the article about Banach-Lie group boys. This lecture is based on these two articles, which are joint work with Pedro Macei. We have here the work by Courage, Mastripieri, and Mbekta. Here is the work in the finite dimensional context of Golub and Pereira, the work by Isumino, and Wedin's formula is in this work. So thank you very much.